we're not going to discuss carbonyls for another few classes, because the next up will be alkynes. And then we'll probably discuss synthesis for a little bit, and then we'll go into carbonyls. So, so with that being said, it's important to recognize, as we're going through these reactions right now, sort of where we're heading with this, right? I think there's going to be a lot of reactions that are going to start being thrown at you guys, and it's just going to seem like a lot of knowledge to have. But eventually what we're going to get to in maybe in a week and a half or so is going to be synthesis problems, where we're actually going to use all of these reactions, and you're going to actually have to sort of combine many of them, sort of bring them through your memory in order to plan multi-step syntheses to get to different targets. And so as we're going through these reactions, I think it's important that you sort of understand the mechanisms, but that you also start now, getting these reactions down, knowing them. It's not necessarily memorizing per se. We try not to memorize, but inevitably there is a component of that to the course. But again, if you can sort of make them seem more alike, then you can sort of remember them by association rather than being their own unique reactions. So I thought that I'd spend maybe the first 10 minutes just sort of going over some of the reactions that we've learned to date. Right, and so for alcohols, now we haven't done all the alcohols in the chapter, right? And so what's going to happen is a little bit later on, we're going to discuss, for example, things like oxidations. There are going to be certain reactions that I think are better taught within the context of other reactions. So not all the reactions that are in the alcohol chapter we have necessarily covered. I'll go over the ones that we have, though, right? And so one of the things that we learned, right, is that we can convert an alcohol into a halogen, right? And so if you guys tell me what is the reagent that we use to, say, convert that into a halogen. Let's say we wanted to convert it into a bromide. So HBr, right? So one option is HBr. That's at least mechanistically the simplest. And then what was the other one? So let's just say HX, right? Because I sort of say X there. So HX, that can be hydrochloric acid. It can be, HI. It can be HBr. So that's option one. And option two is, right? So PBr3. If we want it for bromide. Correct, and SOCl2 for Cl. You may also see oxalichloride. I don't remember if it's in your book or not, but don't worry about that one. Just focus on thionyl-chloride. What's the advantage to one of these over the other? So perhaps stereochemistry, right? You may not scramble stereochemistry. There's also possibilities. It's just, again, if you think about this one, it's likely to go through a carbocation intermediate. And so anything that you might think that might be more SN1-like in terms of chemistry might lead to problems, where in these they have a more SN2-like character to them. So again, if you want to sort of invert stereochemistry, you might want to use these. If you don't really care about the stereochemistry, it might be this. However, you may want to, this is obviously advanced, because I told you guys not to worry about necessarily predicting carbocation shifts, but certainly it's important to know that there is that possibility that sort of like alkyl shifts and hydride shifts can take place in the presence of something like HX, and these can sometimes prevent it. Okay, so that's one of them. We also learned how to convert alcohols into ethers, right? It was actually one of the first reactions that we learned. And so how do we know how to do this? There's a couple ways, right? What's that? So one of them is Williamson ether synthesis, right? And so what do we do in a Williamson ether synthesis? So what's the first step in a Williamson ether synthesis? That's the other one. So Williamson ether synthesis. Right, so you're going to start with, you're going to deprotonate, right? So first sodium hydride, and then you're going to treat it with R prime X, right? The other way that we know to do this, right, is an acid, right? Something like sulfuric acid, some very strong acid. And as I sort of have shown here, that R would be the R prime, but you can imagine if you wanted to do this ether in the presence of this, and you really wanted to force this reaction to make it, you could we only talked about it in terms of dimerization, but again, you could imagine if you used a large excess of some alcohol, obviously you would then get a lot of dimerization of this, but if all you care about is this, you run the reaction in the presence of different alcohol, you can sort of get to unsymmetric ethers, excuse me. Okay, so that's a few of them. Again, many of these are very mechanistically, they should make sense to you guys mechanistically based upon what we've learned. Same goes, very similar to sort of Williamson ether synthesis, right? We learned ways to make oxygen other thing bonds. So we learned how to make, for example, sulfonates. Right, so we learned how to do this reaction, right? And so what kind of molecule is this, whether it's a tosylate or a triflate, right? What kind of character do these often have? What are they similar to? Yeah, they're leaving groups, right? So this sort of group behaves as a leaving group. So oftentimes, if you don't really care about specifically making this compound, if you're using this to get entry into different functionalization, you can oftentimes think of triflates and tosylates as sort of handles for generating leaving groups. And so how do we do this? We use the sulfonyl chloride, right? So we'll use and generally, not always the case, but generally you have some sort of base as well. I'll just say base. It's usually an amine base, something like triethylamine, but the point is that you usually have a base in there. You don't necessarily need it, but you usually have that in there. Alternatively, another type of group that we learned to make, right, was silyl ethers, right? So these are silyl ethers, right? And so how would we do that reaction? We would have some sort of a silyl chloride, right? And so those R's can be different things. This is like PBS or trimethylsilyl. And again, in these cases, it's not always the case that you need it, but oftentimes there's a base in these as well. What is the purpose? So while this one can serve as sort of a leaving group, right? What's the purpose of this? Right, so this is a protecting group, right? And so if you want to protect it, how do you deprotect it? Another thing in there. Yeah, so some sort of, right, exactly. So I'll just say fluoride. So there's a couple different types. We can use HF. We can use sort of sodium fluoride. We can use, there's a organic soluble fluoride that's tetrabutyl ammonium fluoride, right? And this will get us back to there. Okay? All right, and we learned two other alcohol reactions so far. One of them I'm not going to go over this. I did mention this during so I'm actually not going to talk about this one again. We did talk about this during the review. If I take this and I treat it with acid, this is one of those rearrangement ones. You guys remember what this is called? Pinnacle rearrangement, right? And so in the pinnacle rearrangement, again, I'm not going to go through the mechanism, as we already did in our recitation, our review section. So if you're curious about this and you missed that, go back and look at it. Okay, and so this is a dehydrating reaction, so you end up losing water. I'll just write minus H2O again, because that's going to become a theme that we're going to see. Oftentimes, reactions are dehydrative in nature in terms of you drive them by losing water. And that's the case with this other reaction I'm going to mention, right, which is an elimination reaction, right? So if we just want to eliminate water, right, we can convert this to an alkene, usually with some sort of a strong base. So oftentimes your book will have phosphoric acid. Usually phosphoric acid isn't strong enough. Sometimes you use catalytic amount of sort of sulfuric acid. I'll just write sulfuric acid. But again, you'll often see phosphoric acid. I think it's more important to think about that mechanism rather than the specific details of the reagents that are being used there. So And again, that's also a dehydration reaction, right? You're losing water in that reaction. Okay, so this is to date. There are other alcohol reactions in the book that we will get to shortly, but these are the ones that we've covered so far. Okay, now I'm just going to refresh on the alkenes. So you guys should, at this point, if you haven't already, you should know all these, right? So you should be getting to the point, because rather than wait too long, you should be knowing all these reactions, because they're just going to pile up more and more and more and more. So it's best to stay on top of these, really try to know all of these reactions. That's why I'm putting them up here for you guys to say, these are the reactions you need to really know. You need to be able to pull these from your memory. And so that's kind of where you want to get to with all the reactions that we know. And again, it'll make sense why you're doing that, and it'll pay off once we get to synthesis, because you can't practice synthesis problems unless you know all the different reactions. Okay, so we'll go over the alkene ones. Okay, so for alkenes, quiet please. Did I just hear somebody? Oh. Okay, so alkenes, right? So I'll just sort of use sort of these unsymmetric alkenes just to sort of reflect and sort of show a little bit of regioselectivity that we can get here. One of the first things we learned is sort of the opposite, right, of the dehydration reaction, right? So you can go to the alkene from an alcohol. You can also sort of go to an alcohol and an ether in the reverse direction. Right, I think we showed this with water, but certainly if you go through the mechanism, it can happen with any alcohol, in which case you'll generate an ether. Right, and this is going to add that ROH across the bond. Right, and the proton's going to end up here, and the OR is going to be there. So again, that OR, if the R is an H, that's adding water across, but certainly mechanistically you can imagine any alcohol can add across that. We also learned that we can, maybe not with alcohols per se, but we did learn that, at least with water, we can sort of reverse this regioselectivity. So again, if you go through the mechanism, you should understand why we're getting the alcohol on the more substituted, or the oxygen on the more substituted carbon, and the hydrogen on the less substituted. Again, the last reaction we discussed last week, I'll just put it here underneath here, because I think it's a good way to remember this one. I'll just abbreviate NaOOH, right? That's going to be the sort of active agent. Usually it's a sodium hydroxide, hydrogen peroxide mixture that we have there. You do this first, and then you do this one. So oftentimes you guys will see Roman numerals, or sorry, not Roman numerals, lowercase I, lowercase Roman numerals, I guess. Meaning this is all done in the same pot. So you do this one first, and then you do that one. Otherwise, sometimes it'll be like a semicolon. Okay, in this case now we're going to get the opposite regioselectivity. Right, so this is the opposite. This is a hydroboration oxidation. We didn't talk about this. We'll start getting into this on occasion. I didn't bring this up because it's oftentimes really not that relevant. But you should know that this is in fact a syn addition. We did discuss how the hydroboration takes place across the bond, and so you guys should actually know. Again, if you react with a alkene that has some stereochemistry, right, there might be a stereochemical outcome, and you guys should be able to sort of know what that is based upon that hydroboration again, because it's a concerted reaction. Mechanistically similar to this one, right, we learned about adding halogens across double bonds, or not, a couple different ways that we did halogens, but you can do an acidic-like method, right, where we have HX, right, so that could be HBr, HCl. In this case, again, it's going to be this sort of quote-unquote Markovnikov addition, where the halogen will end up on the more substituted carbon. Again, you don't need to memorize that if you think through the mechanism and sort of recognize that the carbocation is more stable, and that's the one the mechanism will lead to. We also learned about halogens adding across by themselves. right? So if we just have X2, right, this is going to add across that bond. And again, it's important that you recognize that it adds across anti, right? So there's an anti-addition when you add, say, bromine across the double bond. And the last one that we have is kind of an example of this, right? It's sort of another sort of extension of this, depending upon the solvent that you use. So if you use an aprotic solvent like dichloromethane, you're going to get the halogen added across. If you use an alcohol solvent, like let's say, whatever, I'll just say ROH. Right, if you have an alcohol in there, now what you're going to get is the alcohol in place of one of the halogens. And again, if you sort of think through the mechanism and the fact that there's going to be partial carbocation character here, that's going to be more stabilized, and it turns out that that's where that alcohol is going to add in. That one's a little bit, I think, trickier to think about, but it's an electronic argument rather than a steric argument in terms of the nucleophilic attack. Okay, so these are all the alkene reactions that we've learned to date. Okay, and so same thing I said with the alcohols applies here. And so we're going to go over, I think we'll probably finish up the rest of the alkenes today, and we'll probably transition to a little bit of alkynes, which will be very similar. Many of the reactions of alkenes will be almost analogous to what we see with alkenes. And once we're done with that, then we'll actually be in a position where we can start practicing synthesis. And we'll go over just some sort of synthesis problems, start getting you guys thinking about putting together synthesis problems, because at that point we'll have enough reactions. And then what we will continue to do is learn new reactions, and the synthesis problems become more challenging because you'll need to use more reactions. And so again, don't wait to get these reactions down. Start now. If it takes flashcards or something, just get all these reactions down and be able to pull them out of your memory. Okay? All right, so the next couple of reactions, unfortunately today we're going to be talking about quite a few reactions that aren't going to be necessarily mechanistically too similar to reactions that we've learned, but we will see some analogies, and I'll try to use these analogies as best as I can. But oftentimes, I think in these types of reactions that I'm going to show you, it's oftentimes a good idea to compare them. In the same way that hydroboration oxidation reaction is, I think that you can sort of remember it by thinking about the Markovnikov addition and sort of saying, okay, if you have acid and water, I can understand that mechanistically. Maybe the hydroboration oxidation mechanism is a little bit more challenging, and maybe it's difficult for me to sort of get that, but I can remember at least the reaction by remembering that there's another reaction that also adds water across the double bond, but it adds in the opposite regioselectivity. And so some of the things I'm going to tell you about today are kind of in that same realm. Okay, so with acid, I'm going to just sort of start talking about acid and water, right? And I'm going to go back to acid and water. This isn't one that I care too much about, but I do think that it's interesting, and I think it's worth teaching. People don't generally run this reaction, so I think in the past maybe I sort of overlooked this reaction to an extent. But if we try to do, again, the same problem as we've seen in the past. If you take, say, an alkene such as the one that I showed you here, and you try to do a sort of hydration of this alkene, and what you might have been trying to get would be this, right? You might expect that you might get this product here. And the problem is, sometimes, when you're doing this chemistry, you can get some problems that could happen, right? And the problem comes, again, through the generation of that cationic intermediate. So when you get the cation, it's a high-energy species, rearrangements can take place. And again, as I said, you don't necessarily need to be able to predict them, but you should recognize that they can happen, okay? And so the thing with a reaction such as the one that I'm showing you here is that once you get to that carbocation intermediate, you can actually do an alkyl shift. Okay, and so this could be a problem if you're running a reaction like this. Okay, and that alkyl shift, I'll just show that carbon moving there. Okay, so this carbon with its electrons. So I'll draw those electrons in. They're going to move right over to this carbon right over here. And when you look at those two carbocations, you might notice that one of them might look a little bit more stable than the other, right? Which one? This one, right? Because it's tertiary, right? And so, again, this carbocation might take place, rearrangement might take place, and what might happen is that instead of getting this product, right, you would have the water add in here. And again, we've seen this reaction a number of times, so for the sake of time, I'm just going to take you there, but you guys should all be able to finish out this aspect of the reaction. If you can't, look back at some of the other, look back at your notes and so forth. But the point is that you're going to sort of get this product. You might end up getting a product that results from a rearrangement, right? And so when you're running reactions and you know, over time, certainly this is a very classic reaction. It's been known for a long time. Yes.
Isn't the only reason the carbocation shift is because we have a poured nucleophile and a poured solvent?
It's the only reason the alkyl
Because we have a poured nucleophile and we have a hydrogen, which is a poured nucleophile, and a poured solvent, which is water. So that's why it's like an SN1 reaction.
Yeah. I mean, this is going to go through a carbocation intermediate. I mean, you can't really generate. I don't think it's. Maybe. I'm not quite sure. So the question is, it's a rate issue that you're getting to. So yeah, so perhaps if the nucleophile is strong enough that it can react with this before carbocation shifts. Yeah, I mean, that's completely possible. I'm not, again, anytime we're talking about alkyl shifts, the point that I'm trying to make with them is that they happen. It's never something necessarily that I would ask you guys, like I've said, I think numerous times, I never necessarily ask you to predict, right? But like you're saying, yeah, maybe there's a better nucleophile, maybe this isn't just water, but maybe it's sodium azide in water, and that carbocation reacts with the azide much quickly. The thing is that intermolecular or intramolecular reactions can generally be a lot faster, though, than intermolecular reactions. So, but yeah, I mean, that's why, again, there's an unpredictable nature to chemistry, and certainly you might imagine that not in every case would this rearrangement happen. I'm just saying that it could happen. And if you're up in a situation where you could have a rearrangement happen, right, there are reagents that you can use to actually get this product, and you can make it without this taking place. And these reagents are actually sort of a hydromercuration reaction, an oxymercuration reaction. And so what you do is you take this alkene, you treat it with mercuric acetate. Okay, so there's mercury and then two acetates. This is one of the reasons why we don't generally use this reaction anymore. Mercury is really, really bad. And so you rarely see this shown or used, but I think it's something that's in the textbook, so I'll show it to you. And I think it does sort of reflect some of the efforts that people have made to overcome some of these problems. But you do this in the presence of water, and there's a second step I'll get to in a moment. But what happens here is that if you draw out the mercury, the acetate actually sort of serves as a leaving group. Okay, so you can imagine the mercuric acetate looking like this, mercury, oxygen bonds on both sides. When you react with the mercury, you're going to sort of lose this acetate. Okay, and it turns out that this reaction is going to look very similar. While in many instances when we're dealing with metals and transition metals, the mechanisms are overly complicated. I think in this case it's not too bad, and I think you guys could all rationalize it because we've seen something very similar to this already. Okay, so we're going to lose the acetate. And it turns out in this case what actually happens is, and this sort of goes back to a rate issue, right, is that if you have mercuric acetate, this will actually help stabilize that cation. Okay, so it turns out that the carbon-mercury bond is really strong. Oftentimes you can just redraw this, similar to the bromonium stabilization. So that's oftentimes how the book will write it. And so what you'll do is you'll put a positive charge on the mercury. It doesn't necessarily look exactly like this. But this is a good way to, I think about it, right? Because it's very analogous to what we saw with bromine, right? And so it just so happens that in this case, the way that the mercury reacts with this reaction, that cation is not going to migrate as quickly because of other components that are taking place. Now, when you're at this state, what happens is very similar to the bromine reaction, and that's that the water is going to add in. It's going to add in the same way that the bromine does, right? So there's going to be an electronic control here. Okay? So that's very similar to the bromine reaction that we saw. So it's actually anti-addition across this. But it turns out that that doesn't really matter at all because we're going to chew this guy off in the next step, right? Because what we're trying to do is we're trying to add water across this. We're not trying to add mercury and water, or mercury and OH across this. And so what we're going to do is we're going to get to this water here, just to sort of complete the mechanism. We're going to deprotonate one of those, and we're going to get to this compound here. And then it turns out, I won't go through the mechanism of this, but it turns out that this is a pretty good nucleophile. This sort of mercury-carbon bond is fairly nucleophilic, and you can actually reduce this off. And again, this part of the mechanism I won't worry about. But you take this and you treat it with sort of reductant, which in this case is going to be sodium borohydride, which is one we'll see from time to time. And this will actually reduce off, so I reverse that. I take that back. What we're actually going to do is we're going to reduce this. So imagine a hydride adding in here. This is actually, I don't want to get into the metal chemistry, but the net result is you get mercury 0. That's really not that important at this stage. But the point is that you end up getting water across there, and you can actually prevent this. And so this is another option, to add water across a double bond. Again, you guys have a lot of reactions to learn. And so, but again, this is, I guess, it's very similar, I guess, to bromine. So it's, I guess, worth thinking about. But again, this is just sort of to illustrate that oftentimes when we have these issues and we have these rearrangements and we have these problems, we oftentimes have many, many, many different ways to do reactions, because sometimes only one of them will work. And so this is just one example of how problems with a specific reaction that might look simple has issues, and how chemists have sort of come up with alternative ways to do this. And I know that there's actually, like, a friend of mine is actually working on trying to come up with ways to do this that don't involve, like, mercury. And so currently you still have, like, chemists trying to figure out ways to do this that don't involve such toxic metals, and so that more likely people will use them. Yes?
How did you get the mercury acid off?
So what happens is formally what happens is sodium borohydride, we'll get into that in a minute. You can sort of think of it mechanistically as H-. That's not actually how it works, but at least from a mechanism standpoint, you can think about it as a hydride, so hydrogen with 2 electrons. I don't want to get into too much details on the metals per se, but you asked, so I'll just sort of show you really quickly. Mercury in this case is what we call an oxidation state of 2. Okay, so it turns out that what you can do, space, right, when you have mercury in this state, technically it's considered a 2 oxidation state. Again, this gets into inorganic chemistry and organometallic chemistry. And so what that means is that if you can sort of give it 2 more electrons, it might be happy, right? And so what you do is you can reduce that, so that sort of oil rig, oxidation is loss, reduction is gain. So you're going to actually reduce this and give it electrons. And formally, you can think about it like this. Okay, so the net result is that it's going to basically go from sharing 2 electrons to now sort of owning those electrons. So again, this is organometallic chemistry. I don't expect this to necessarily make sense or for you guys to know that, but you asked, so that's, I think, the way to think about it. Net result, mercury 0 plus an acetate. Okay. Okay, so that's an oxymercuration reaction. Again, formally the same thing that you would get here, but again, it sort of illustrates how there can be these rearrangements and we can see problems, and chemists have come up with ways around them. Similar to how thionyl chloride is an alternative to treating something with HCl, right? Okay, so that's the first reaction of the day. Oh, we gotta move. Okay, so last week, again, and I sort of discussed again today, how the addition of water, right, across the double bond, right, if you use acid and water, it leads to one way, and if you add borane and hydroboration, you can sort of add water the other way, right? And it turns out that there's a neat trick that you can do to actually add HBr across the other way. And so again, in a standard HBr reaction, right, the addition that we're going to get, right, is that we're going to get HBr addition across in this sort of fashion. Again, go through the mechanism, see that you have this buildup of positive character on that carbocation here, so you're going to have a carbocation and it's going to add in. And so in the same way that the question the chemists come up with when they have this, again, this is sort of very simple, an HBr and an alkene, it works, but then chemists sort of ask the question, well, and again, this will come in with synthesis if you want to make a certain thing, well, what if I want to add the other way? Okay, so the question is, how might I add the other way? You know, let's say I want to add it the other way. How do I add it the other way? And it turns out that if you run this reaction in the presence of peroxides, you can actually do this. And I'll go through this mechanism fairly quickly. It's going to involve radicals, which we haven't really discussed yet. We'll discuss in a little bit more detail later on. But I'll go through it once now so you can be exposed to it. And then hopefully down the road, when we're actually talking about radicals, maybe we'll revisit this if we have time, and it might make a little bit more sense. Okay, so radicals are different ways. So if you read the mechanism chapter in your textbook, it discusses the two different ways that we can draw arrows, right? And so anytime, pretty much all that we've drawn to date, right, has been arrows that are sort of double-headed, right? So that they sort of have a standard arrow, and that means 2 electrons. Right? And so everything that we've seen today involves 2 electron pushing. One of the ways you can call this is heterolytic bond formation. So you'll talk about like heterolytic bond cleavage, like if both electrons are going with it. But alternatively, radical reactions we draw a little bit differently. We do sort of a half arrow like this. Okay? And this is going to be how we're going to show the movement of a single electron. Okay, and so this is what we'll call homolytic bond cleavage. Okay, and radical reactions often require that we're going to use this homolytic bond cleavage. For reasons that I'm not quite sure about, oftentimes many students that have trouble with heterolytic bond cleavage, sometimes homolytic bond cleavage makes a little bit more sense to them, maybe because instead of moving 2 electrons, 1 is a little bit easier. But surprisingly, while this is sort of brand new, this is usually something that makes, at least in terms of drawing appropriate mechanisms, students seem to have a little bit better time doing. Okay, so what we're going to use when I show this mechanism, okay, is I'm going to sort of choose, I'm going to be using these single electron arrow pushing, okay? Okay, so the mechanism. Okay, as I'll get into with the radical chemistry, there's a sort of process that we go through that says, you know, sort of initiation, which is sort of how we generate a radical. Then there's a propagation step. That's basically the radicals doing all its thing. And then there's sort of a termination step where you sort of kill the radical. And so I'll try to do it in that way, just to sort of stay consistent. With the sort of initiation step, it's going to be the one that we're generating this radical. And the way that the radical is generated, as you might imagine, is that new thing we've got in there, right? The only difference between this is that we've got peroxide. So that peroxide is going to be what sort of initiates the radical process. It turns out that homolytic bond cleavage of an oxygen-oxygen bond is okay. And what you get is, I'll color coordinate this. Right, so when we're going to break that bond, right, usually you're going to sort of show 2 of these sort of half arrows. Right, so what's showing is that there's 2 electrons in there. One of them is going to go to one oxygen, the other one's going to go to the other oxygen. Okay, so this is the sort of initiation step. Okay, and obviously we have 2 of these. I'm not going to show both of them. One of them would be a blue dot, the other one would be a red dot, and so we'll have 2 of these guys. And so this is the initiation. This is how we're going to generate the radical. Okay? Now during the propagation, what we're going to do is we're going to start moving that radical around, and when I get to the point that's important, I'll sort of tell you. May have misspelled this, I don't know. Okay, but what happens is the radical, in this case, is going to react now with the HBr. Okay, and it turns out that what's more stable in this is going to be the bromine radical. So again, bromine is bigger, it can sort of stabilize this radical a little bit better. So it turns out that halogen radicals are okay, not great, but that's what's going to happen here. We're going to generate an alcohol, okay? Okay, and then again, notice how we have one arrow going here, the other half arrow going here. So again, the two electrons going into there are sort of splitting. One is going to form the bond. The other arrow, the other electron is going to go to the bromide. Okay? Okay, so the board space is going to have to come over here. Radicals? Yeah. Radicals are, Radicals are very fast processes. Because a lot of things can happen, right? Like this can go back and forth, back and forth, back and forth, back and forth. But once you generate a little of this, maybe at some point it'll react like this. It's chemistry, right? It's lots of things are happening, and you hope that enough of the things you want to happen will happen, right? So at this point now, the bromine's actually going to react with the alkene. Okay? And this is where, this is sort of the important step here. This is the part that actually dictates the regioselectivity that we're going to get. And so if you can imagine two possibilities here, right? Because this is the part where you can either put the bromine on one carbon or you can put the bromine on the other carbon. Right? And so here's one possibility. The other possibility would be this one, right? And so if I sort of draw these products, right, we're going to get to this radical, okay? In the other case, we're going to get to this radical. Okay, so while I'm trying to find a new piece of chalk, think about which one of those you guys might think might be more stable. And when I ask that, again, we haven't really seen radicals yet, but I would ask you, do you think a radical would behave more like an anion or a cation? Would a radical behave something that's electronically rich, or would it behave more like something that's electronically poor? How many people think electronically rich? How many people think electronically poor? Okay, so somebody that's saying electronically poor, why do you think it would be electronically poor? Doesn't have a full octet, right? Exactly. Right? So it doesn't have a full octet, it wants that full octet. So radicals, in many ways, we'll see radicals will behave like a cation, right? Because it's electronically poor. And so as you might imagine, the top one is actually going to be a more stable radical, right? And this for the same reasons that a tertiary carbocation is more stable, right? So you've got this hyperconjugative effect, which is going to stabilize this radical, okay? The final step in the reaction, right? So again, lots can happen, and there's many different ways that you can sort of write within here. But let's say, for example, we take the ROH, right, just to sort of stay consistent. So we'll go with that ROH over there. Okay, and we'll sort of go back to right? So this is just this radical's reacting with the one electron. So it's a sort of bond that we're making. I just sort of drew it upside down, kind of like Top Gun when he's flying upside down. Right. So okay, so here we have I was flipping the bird. Okay, so this is how you're going to get the regioselectivity, right? So now what's left over is this guy. The sort of termination step is, that radical is likely going to go away at some point, and so again, over here we had two equivalents, so you might imagine the termination step would be that sort of going back and generating a single one. So we're not going to see another radical reaction for another month or so. So I wouldn't stress too much about this mechanism at this time, but hopefully I wanted to show it to you guys. And I wanted to show it to you guys now because I think this is the point where you'll remember it, right? Because if you can add HX across it one way, in the same way that hydroboration, I think it's best to think, I can add water across an alkene one way. I can also add water across the alkene the other way. I think that's often the best way to sort of remember this specific reaction. Coincidentally, they both kind of also involve peroxides, and so whatever. However you can sort of associate them with one another. But again, this is going to get us to this sort of anti-Markov-Makov addition of HBr. Okay? So again, radicals, I wouldn't necessarily worry about mastering radicals right now. We'll get back to more radicals later on, but at least what I would like you guys to sort of see here is why there's the selectivity that it is, and at least we can start thinking about radicals being electronically poor. Yes?
I don't understand. Why is the first one you wrote more stable? Why is it more stable?
So a radical, that's what I was asking, is a radical electronically rich or electronically poor?
You said it's missing again.
Right. So it's electronically poor. And so it's going to behave more like a cation, which is electronically poor. Right? So in the same way that a cation is electronically poor and an anion is rich, right? The sort of same factors that you sort of associate cations and radicals instead of in terms of relative stability. Okay? Yes? Quiet, please. Yes? Yeah, so the propagation is everything. It's like a sandwich, right? Bread, meat, other slice of bread is the termination. Okay? All right, so lots of complicated mechanisms today, but again, you can sort of see, hopefully, now you sort of know a little bit about radicals, and now you know a new way to add HBr across the double bond. That's the important take-home point here. Okay? So again, I'll just say it one more time so that people aren't coming and asking me. The mechanism, I don't even know that you'll necessarily be responsible for radical mechanisms on the next exam. So of everything from that, know that reaction. And again, if you sort of understand radicals and they make sense, then more power to you to sort of rationalize it that way. But we'll return to radicals. I think it'll be the last reaction we'll discuss. Okay, so I'm going to talk about a couple more reactions of alkenes. Okay, now we're going to start getting into a little bit of what's called oxidation and reduction chemistry. And again, these are going to be reactions that are mechanistically a little bit more complicated. I'm going to sort of show you the mechanisms, and many of these you won't be responsible for. But I think it's good to show them because there are certain stereochemical outcomes to some of these reactions that are relevant here. Okay, and so the first one I'm going to show you is actually a dihydroxylation, right? So we've seen that we can add water across the double bond, right? We've seen that we can add, it's almost like one carbon is going to be a halogen, one carbon's, either a carbon can become a halogen, a carbon can become an oxygen, a carbon can become a hydrogen. And so what we're doing is almost like a mixture of all of these at this point, right? And so we've had oxygen on one side and hydrogen on the other. What I'm going to show you now is how to put an oxygen on both sides, right? So what we're going to do here is what's called a dihydroxylation. Okay, so somebody asked earlier something about this reaction in the presence of a different reaction, but there is a way that we can do this that it's not just acid and water. And it turns out that this way that we run this is with a reagent called osmium tetroxide, deadly compound. And then what we're going to do, you're going to see it's going to be a two-step process. Again, the second step is actually going to be a sort of I think it's best to just think about it as a hydrolysis. I think that's probably the best way to think about it. Technically, it's more of an oxidative process, so HSO3 plus water. But again, I think that you can reason the second step just through standard sort of hydrolysis, and I'll sort of explain that to you in a moment. Okay, so how this works is osmium tetroxide is a very high oxidation state compound. So we were talking earlier about, in the case of mercury, how mercury had this oxidation state of 2, and then sort of in that last step it became 1. In this case, osmium, again, you don't have to get into this. If you want to learn more about this, you can take a sort of an organometallic class or an inorganic class, but this is actually an oxidation state of what we call 8, so this is very high in oxidation state. This is the sort of point that I'm trying to make here. Okay? And what happens is oftentimes in metals, you're sort of going through these sort of high oxidation states, and then you're sort of going to perhaps a lower oxidation state, and you're sort of shuffling through oxidation states. Again, you're not responsible for this mechanism, but I'll sort of show it to you. What happens here is that you're going to make a bond. I'll try to map this, guys, out for you a little bit. I'll make this one orange, and I'll make this one blue. Okay? And what's going to happen here is when you do this, it's going to go from an oxidation state of 8 to what's called an oxidation state of 6. Okay, and if I sort of map the electrons, again, I recognize this one's a little bit more complicated to see. These electrons will now be over here. These electrons will be making the bond with that oxygen. Okay, and again, I think that's the important part of this. Again, even you're not responsible for that mechanism, but you can sort of see how through this mechanism what's happened is that we've gotten 2 oxygens there. Right, and those are going to be the 2 oxygens in our product. Okay, and so the final step is a little bit more complicated. I think it's best if you just think about it as a hydrolysis. I wouldn't worry too much about this, but we're going to sort of cleave off that osmium part of it. And what's going to happen here is you're going to get to this. And so, again, perhaps if you just sort of think about it as water displacing that other oxygen there. Maybe that's the best way and the simplest way to sort of rationalize it from a mechanism standpoint. It's a little bit more complicated than that, but of course it's already complicated enough, right? So if we just sort of think about it as, water kind of exchanging out with that. And again, you'd be protonation, add in, sort of SN2-like, but you could probably go over that on your own and sort of see how that might happen on both ends. Important point here is a couple things, right? So these oxygens are the ones that actually come from the osmium tetroxide. There's an important aspect of that. Would you think, based on looking at the mechanism that I drew there, that this would be a concerted reaction, or would this be a syn addition, or would this be an anti-addition? It'd be a syn addition, right? And so, as you might expect, in cases where we could have a mixture of stereoisomers, like let's say cyclohexene, right? If we did the osmium tetroxide sort of reduction reaction, you could imagine getting 2 diastereomers. Right? But since we know that it goes syn, which one is going to form? Top one, right? So if you do an osmium tetroxide oxidation, you get to this sort of syn. So there is a stereochemical outcome. And again, if you can at least, even if this doesn't completely make sense to you, you can sort of remember how those 2 oxygen-carbon bonds are kind of forming simultaneously. And that will hopefully at least, I think the important aspect to note here is that the sort of reaction here actually leads to a certain stereochemical outcome. So again, if you're going through a synthesis problem, this might be the way that you would do this. I'm actually going to completely divert right now, as I'm sort of saying this, to a different reaction that I didn't write down, but I think it's worth mentioning now. I don't know when I was going to mention this reaction, but the question becomes, like I've been constantly saying, well, if one reagent leads to one thing, how might we get to the other thing? Okay, and we'll discuss this, yes? What's that? Yeah, they both leave, so then a water would attack on the other side as well. At least, I think that's the best way for you guys to think about it at this point. What's that? This is a lot of water around, so the water would do it on both sides. So you got lots of water around. So the same thing I drew over here would also happen over here. I don't want to, in the sake of time, I'm not going to show it to you. But the question is, how might we get to the ante? And there is a way that we can do this, okay? But it's actually going to be a two-step process. And I think I'm going to bring this up again later on in the semester, but I think now's the time to sort of bring it up. You can actually, it's a two-step process. What you can do is you can actually convert, so this isn't necessarily analogous to what we showed before, but I think this is worth showing you guys now because it's a strategy to get to the other one. And I'll show this again later on, but it's at least good to sort of, I think, make that comparison now. And again, how this works we'll talk about later on, but maybe now it's at least the first introduction to this reaction. We can sort of show you guys here. You can actually generate these molecules called epoxides. Okay, so again, I'll talk about this later on. I wouldn't worry too much about this except to recognize that you can do one way or the other. So if you want to get to the syn, you can get to the syn. But since I just made a big deal about the fact this leads to the syn, I think at least now it's worth just briefly mentioning that you can also get to the ante. So you'll do this reaction called an epoxidation, which we'll talk about later on. And then the second thing that you'll do is you would treat this with, say, acid and water. Right? Or sodium hydroxide, for example. But usually acid and water will work pretty well here. And then again, this is going to be very much like the bromine reaction, right? When we had a bromonium ion and the oxygen added from behind it. So that's what's going to happen here, is that you're going to... Okay, so everybody sees how I did that second step, right? It's going to add from the back side, and so that's how the stereochemistry is going to come out. So similar to the bromonium, so sort of related to the bromonium. So again, this first reaction, I'll talk about a little bit later, but I think it's at least worth mentioning this now, and we'll mention it again later as well. So it's just you can get to the syn, you can also get to the ante. Okay? All right, so that's osmium tetroxide and dihydroxylations. Okay. I am like out of chalk here. Okay, so we can add oxygen across both bonds. The last thing that we really haven't discussed, right? So we've added X2 across the bond, we've added water or ROH across the bond in both ways, right? We've added sort of OH across both bonds. We've added H and X, two X's, one of those I think I already said. The one that's missing, right, is two hydrogens, right? That's the only thing, if we just think about halogens, oxygen, hydrogens, we've sort of had a combination of all of these, and the only one that we really haven't talked about yet is if we want to add hydrogen across this. Okay? So that's the one last one that there'll be one more that I'll talk about, but at least in terms of additions across alkenes, right? Again, all the stuff that we've done so far is addition across alkenes. And the way that you do this is actually, again, fortunately this isn't one that has a really, I think, mechanism that will sort of flow with everything else. That's sort of the theme today. But what you're going to do is you're going to use hydrogen gas. Okay, so that's going to be your source of the two hydrogens that you're going to add across. Okay, and then you're going to have some metal. And so it turns out the way that you do this is you do metal catalyzed hydrogenation. Okay, and so that metal can be a number of different things. One of the classic ones is palladium on carbon. Okay, So you'll see sort of, this is a very common reaction. You sort of just have a sort of a slurry of palladium and you bubble hydrogen through there. And you can reduce double bonds or think about it as add hydrogen across that double bond. How does this work? There's not a great way to show the mechanism. I'll show you, I think, one way to think about it at least. That's not completely wrong, but it's also not completely right. Again, in metals, I don't want you guys worrying too much about metal-based reactions, and so you're not responsible for this. But when you take palladium 0, so that's sort of 0, that's palladium 0, when you take it and you bubble it through hydrogen, what happens is you get to palladium 2. I'll try to teach this from the standpoint that's going to sort of explain to you the stereochemistry, because there is stereochemical outcomes, so the same way as the osmium tetroxide. And what's going to happen here is now this is going to be active species, right? So hydrogen itself will not react with an alkene. But in the presence of a catalytic amount of palladium, this will react with the alkene. Okay? How that happens is a little bit complex, but I'll just sort of show it to you as simply as I can. Okay, this is actually sort of what we might call a sigma bond metathesis. Okay, we're going to have that alkene add across in this sort of fashion. I'm showing it this way because I think it's analogous to something that we've seen in the past. What have we seen in the past that kind of looks like this? BH3, right? So that's one of the reasons I'm showing it this way. It's not exactly this way, but at least in terms of relating it. And certainly BH3 is a syn elimination, which we'll get into in a moment. Okay, and so you'll have hydrogen on one, and then you'll have a carbon, palladium, hydrogen on the other. And then what happens here is something called a reductive elimination. Again, it's mechanistically not that important at this point. It's actually very mechanistically important. To you guys, it's not that mechanistically important. Well, what happens is you do this thing called a reductive elimination. You're going to go back to palladium 0, and you're going to basically have that hydrogen on that carbon. Okay, and then the net result is you get back to palladium 0. The palladium 0 can then insert, and so again, it's a catalytic reaction. You only need a little bit of the palladium, and you can do this reaction over and over and over again. Okay? The important part is sort of this. What's that? So the important part is sort of how the addition adds across here, right? And so it's a sort of a syn addition. And so it turns out that in the same way that that say hydrogen, or sorry, excuse me, in the same way that say the borane hydrogen bond adds across in the syn addition, palladium and hydrogen will add across in the syn addition. So in this case, there's 2 hydrogens there, but let's imagine we had 2 methyl groups here, right? If we wanted to take this reaction and reduce it with hydrogen and palladium, what's going to be the stereochemical outcome if it's a syn addition of hydrogen? Right, so the 2 methyl groups will end up being cis. So, again, if we think about the 2 hydrogens coming from the top, the methyl groups are going to be towards the back. What's that?
Why would it be like EV over carbon?
Why is the palladium on carbon? It doesn't have to be. There's like palladium oxide catalysts that you can use. There's many, many different metals that can actually do this. Palladium and carbon is just, I think, one of the classic ones. I actually don't know the history of it, but it's maybe easier to work with. But it's actually not, because it'll just catch fire if you're working with it on your benchtop. So I'm not really sure why. You know, it's one of those. Again, there's lots of other metals that can do this, but this is like one of the classic ones. So certainly other palladium can do it. Yes. Yeah, so you could draw it the other way as well. I'm actually not 100% sure which electrons. I could have probably drawn it in a reverse way as well, right? I could have had these electrons going after the palladium and these go to the hydrogen. I'm actually not sure which one it is. But that would be that. Yeah?
Why would it have to be syn?
So when the H replaces the palladium, it's just a sort of a concerted process, and you maintain that stereochemistry there. Yeah, so it's the same thing with like the borane, right? It's like the borane is there, and then when you oxidize that borane, you put a hydroxyl in the place where the borane is, you sort of conserve that stereochemical integrity. Or that stereochemical integrity. You conserve that stereochemistry. The oxygen ends up where the borane does. In this case, that hydrogen ends up where the palladium does. Turns out it doesn't matter from a stereochemistry standpoint here, but it does in this case. Yes?
It talks about the possibility of trans isomers forming based on like another alkene.
Yeah, so that's getting to a little bit more complexity. So once you have a palladium species, if there's something nearby, like an alkene, there are ways that you could imagine actually switching where that palladium is. That goes back to the question that was asked earlier, right? Yes, when you add complexity, other things can happen, and certainly if, this is sort of a simplistic version of it. If you want to talk to me about a specific example in the book, we can talk about it a little bit more in detail, but I just want to show you guys this right now. But yeah, other things are around, builds complexity, other things can happen. Palladium's complex in the fact that it can do a lot of stuff. But this is just a straight, boom, you're there. Okay, yeah?
Wouldn't stereochem, it wouldn't matter in that reaction because
Right.
it's already chiral.
Right. Right. And again, that sort of question was asked about chirality. If you were somehow, I can't think of one off the top of my head, but if there was an alkene that, say, wasn't symmetric, like maybe something like, or actually, let's say this, right? If you say had that, that's a bad example. Well, no, because that's, I don't know, I can't think of anything right now, but if there was an example, like you can certainly do hydrogenation and get stereochemistry. Absolutely, but you have to have a chiral catalyst. Okay, I want to get on to the last reaction. Any more quick questions on this one? Yes. Guys, can you quiet down, please? I'm having trouble hearing. That's what we just said earlier. There's lots of different metals that can do it. Palladium is one of the ones that we're showing you guys. So, yes. What's that? This is. Yeah, that's. It's a chiral. But yes, if there was, if that's what I was saying, if it was like this, for example, we might get a mixture of this and like right. So it would depend upon the complexity of the compound. So certainly the hydrogen in theory could attack the hydrogen could attack from either face, and so there are some cases where you get a selectivity issue. All right, so the last alkene reaction we're going to learn today is one that's last alkene reaction we're going to learn is one that's actually pretty neat. Again, I promise that we'll get back to reactions that are mechanistically more simple. But this is one that's pretty neat, and I'll show you this mechanism. You'll learn a reaction next semester that it's called the Diels-Alder reaction, and you might look back at this and you might see how there's some comparisons between the two. But this is a reaction called an ozonolysis. Okay? And this is going to involve, this actually, if you look at the osmium tetroxide mechanism, there's a lot of similarities between the first step in an ozonolysis and the first step in an osmium tetroxide oxidation. And so maybe I'll just show the osmium tetroxide one again. So just to sort of remind you guys, that's sort of the osmium tetroxide, how we get this sort of osmium tetroxide mechanism on there. Turns out that ozonolysis is, at least in terms of arrow pushing, it's very similar. So some of you may struggle sort of drawing ozone, right? But that's what ozone's going to look like, okay? And in the same way that we sort of do this, we give electrons to that oxygen, here the first step is actually going to be driven by electrons to that osmium. In this case, we're going to see that this sort of electron arrow pushing is actually going to help us push electrons onto that oxygen and make that oxygen go from a positive charge to a neutral charge. Okay, so this is highly reactive stuff. You guys know what ozone smells like? Yeah, little tidbit there. Rain. And anytime that smell of rain, that's ozone. Yeah, some atmospheric thing, I don't know. It's like somehow the ozone levels are higher like right before rainstorms. Okay, so what you get to is this intermediate here. Okay, so I would say that unlike the osmotic tetroxide one, I would make this in the same way. I would treat this one similar to the hydroboration mechanism. So this is fair game for an exam. Okay, but it would be one of the more challenging ones. So I wouldn't, if you're struggling with some of the earlier material, don't stress out about this right now. But I'm going to show it to you because I think it's worth sort of going through it, specifically because you're going to see some reactions that are at least similar next semester. And again, it doesn't involve a metal, so you can sort of see how that's becoming a neutral charge and stuff. So I think this one's reasonable. But again, it is harder, so if you're struggling with more simple mechanisms, don't stress out about this one. Okay? So I think getting from here to here is fairly simple. Not fairly simple, but I think that you guys could see it. Even if you did it sort of stepwise and broke it down, you might be able to get there. Next thing that's going to happen is we're going to actually break this down. Okay? And we're going to get to this intermediate. There's going to be a two-step process here. It's going to involve formation of this Kriege intermediate, is what it's called. You can imagine this double bond reacting in one of two ways. Or sorry, you can imagine two different isomers of this forming. I'm actually not 100% sure which one would form, but I would imagine it would be this one. Okay, so what we're going to do here is I'll actually draw it. Actually, there's no way to draw this rather than conserve it. Okay, so there's a lot going on there, right? So I'll walk you through it very quickly, very brief, or sort of a little bit thoroughly. So what's going to happen is these electrons that are on the oxygen here are going to go down and form an oxygen-carbon double bond here. Now, you can't have 5 bonds to oxygen, right? So we're going to have to break a bond there, right? The bond that we're going to break is going to be this one right here, okay? That's going to push an additional set of electrons onto that oxygen. Now, how many electrons is that oxygen going to have? 10, right? So we can't have 10 electrons on this oxygen. So the last thing that happens is we're going to push these electrons here up into that oxygen. So unfortunately, I can't break this down for you guys because that would involve making very, very bad intermediates. But what I'll try to do here is color coordinate it for you guys a little bit. Okay, so that's going to be the one component that's sort of over from this carbon, right? And the 2 electrons that were here are now there. And again, so this becomes positively charged. This now takes on an additional that sort of set of electrons. It becomes negatively charged. And then in this case, this is 2 hydrogens. It's formaldehyde. And so you get to this. And it turns out that what you do when you run an ozonolysis is you actually run it in the presence of a reductant. Okay? Just sort of doing this fragmentation, you can sort of see how this molecule sort of leads to 2 carbonyl-like compounds. It turns out that, in fact, these two now will react with each other. I'm not actually going to go through that. You can look at it in your book. That's what leads to what's called the Kriege intermediate, but that makes it a little bit more complicated. I think this is a part to sort of know, right? Because now you're getting to 2 carbonyl-like molecules. Now these start to resemble the products. Oh, I didn't even show you guys the products yet. Okay, so now you can see that we're starting to get looks very similar, right? The only thing that we need to do is break this oxygen-oxygen bond. And the way that you do that is there's generally a reductant in here. And so sometimes it's run with like, I think zinc sometimes, or triphenylphosphine. I'll show it with DMS, dimethyl sulfide. Okay, and what this is going to do is the sulfur here can actually react. Some of you are going to say, why does it want to do that? Okay, this isn't how the mechanism works. Again, it goes through that Kriege intermediate, but I think this is the simplest way to get there, and so I think this at least should make sense to you guys to a certain extent. The net result of that being that you'll get to these two compounds here. And the leftover compound is this compound here. Do you guys know what this is? Anybody know what this is? Yes, dimethyl sulfoxide. So it's DMSO. Sometimes you guys will see really polar solvents. This is like one of the most. This is a fairly common solvent, DMSO. Okay. So anyway, so the reaction generates this DMSO, and you can get rid of the DMSO afterwards. Okay. So I think I'm going to stop there. I do want to make a quick announcement. So next week we're going to go through alkyne chemistry, and I'm thinking that it may take a little bit longer than one class to go through the alkyne chemistry. But again, I would I know that there's some more complicated ones today. You may want to start really thinking about them and get those ones down. Some of these you may really need to memorize. The other announcement that I wanted to make is that today during office hours, I am going to have to cancel, or not cancel it, but I'll have to stop it at like 12. So normally I know I go a lot later, but today I have a couple deadlines I need to make for different stuff, so I've got to throw people out at 12. So, okay?